In this video, we're going to introduce the concept of a ring. So a ring is another type of structure we encounter in abstract algebra, along with a group. And what makes a ring different from a group, if you had to state it in just one sentence, is that a ring has two operations, addition and multiplication. So here's the definition. A ring is a set, which for now we'll call R. Okay, R for ring. I know you're so used to saying G for group. Now we're R for ring. A ring is a set R with binary operations of addition, which typically I will call plus, and multiplication. And for reasons I'm going to talk about later, I'm not going to state a symbol for that. I mean, we could call multiplication star or something. We're not going to use that symbol most of the time. We will use the symbol dot, but not exactly for the multiplication we're describing here, but more on that later. So a ring is a set with binary operations of addition and multiplication, satisfying the following properties. And here are the properties. There's going to be 8 of them, which is a little bit more than in the text, but the text assumes that we all know what we mean by binary operations. And I'm going to actually incorporate those explicitly as properties in this definition, even though we don't need to. I mean, we could just say binary operations and be done with it and leave off the 2 properties. But anyway, here they are. So number 1. For any x and y elements of R, there is a unique element, x plus y. In other words, we can add up any 2 ring elements and get a ring element, and we will always get the same ring element if we're adding the same 2 things. Number 2. For any elements, x, y, and z in the ring, x plus y plus z is equal to x plus y plus z. In other words, addition is associative. That's number 2. Number 3, there exists an element 0 belonging to R. Sorry, that's supposed to be just a regular 0 there. 0 belonging to R such that for all x in the ring, x plus 0 equals 0 plus x equals x. And that 0 is called the additive identity. Okay, so we have a set, and the operation of addition on that set, first of all, the set's closed under addition. Okay, the addition is associative, and there's an additive identity. And you may be able to guess what the next property is going to be. For every, I'll just say for each x belonging to the ring, there is an element negative x also belonging to the ring, such that x plus negative x equals negative x plus x equals 0. I'm going to try as much as possible not to call this negative x, because I feel like that's a little bit misleading sometimes. I like to call it the opposite of x. So the x plus the opposite of x equals 0, opposite of x plus x also equals 0. That is called an additive inverse. So R has additive inverses. And at this point, you're probably thinking, wait a minute. These are the 4 properties of a group. And you're right, these are the 4 properties of a group. R is a group under addition. It's just going to have some additional structure. One of the additional structures that it's going to have is not only is the addition associative, has an identity, and has inverses, it's also commutative. For any x and y in R, x plus y equals y plus x. So really all of these other things that I stated, like x plus 0 equals 0 plus x, and that x plus opposite of x equals opposite x plus x, those were redundant. I could have just said one of these things each time, because the addition is going to be commutative every time we talk about a ring. So these 5 properties together imply, and there's going to be a couple more properties, or I think 3 more properties, but these 5 together imply that R is an abelian group under addition. Okay, if you wanted to just state the first 5 properties as one property, that would be what you would say. But we're going to lay these out just so that we remember we can use them all. Okay, next property. Number 6. For any x and y belonging to the ring, there is a unique element called xy. Okay, we could call that x star y, but usually I'm just going to call it xy. I'm not going to use dot for this, at least when I can help it, because we're going to use dot to mean something else, which will be revealed later on. But this is saying that for any x and y, we can multiply x and y. In other words, R is closed under multiplication. Multiplication is a binary operation. So again, just as a reminder, number 1 and number 6, I didn't technically have to state those. If I say R has binary operations of addition and multiplication, then that statement implies properties 1 and 6. Sometimes, though, it's just nice to have all of these laid out in a nice little row. Okay, so this is closure under multiplication. And while I'm at it, I'm going to label the first property closure under addition. There we go. Okay, next property, number 7. For any x, y, and z in the ring, xy times z is equal to x times yz. In other words, the multiplication operation is associative. And finally, number 8. For any x, y, and z in the ring, x times y plus z equals xy plus xz, and y plus z times x equals yx plus zx. In other words, we have a distributive property. And this is the only property in the definition over which addition and multiplication interact. So this tells us that there is a relationship between addition and multiplication. And that relationship is, if I multiply something by a sum, that's the same as if I multiply this factor x times each term of the sum, sort of like you learned in high school algebra. And it's same the other way. If I multiply a sum by x, then I can do that by adding up the sum of each individual term times x. By the way, why do I need those two different properties? Well, there's a very good reason for that. The reason is, you'll notice that here I have no property, nothing at all that tells me multiplication is commutative. Nothing tells me that here, and multiplication doesn't have to be commutative. So these are properties of multiplication. But note that multiplication needn't be commutative. Okay, so a ring requires addition to be commutative, but not necessarily multiplication. Now there's another thing though too. So this is just the definition of a ring. But you might think, okay, well maybe there's some kind of special name that we give to a ring where the multiplication is commutative. Like maybe that's an abelian ring. And you'd be on the right track. We don't really call it an abelian ring though, we just call it a commutative ring. So R is commutative. If for all x and y in the ring, xy equals yx. But that's not one of my required properties. And one more thing too, you notice that multiplication is a binary operation. In other words, R is closed under multiplication. Multiplication is associative, and there's a distributive property, which, by the way, the reason we need it too is because we need to know that we can distribute something on the left, a factor on the left, but also a factor on the right. If we had a commutative property for multiplication, these two would be redundant to each other. Okay, but we don't have anything here that says that there has to be multiplicative identity. So that leads to another name for a special kind of ring. R is a ring with unity if there exists some element, which I'm just going to call 1 in R, such that for all x in R, 1x equals x times 1 equals x. And you'll notice I include both because having a ring with unity does not require me to be commutative. So I could have a non-commutative ring with unity. I could have a commutative ring without unity. I could have a commutative ring with unity. There's lots of possibilities. Well, actually, I guess there's 4 possibilities because there are these 2 special properties, and I can either have each of them or not have each of them. So I guess that's really 4 combinations. But really, all of that doesn't matter too much because most of what we're going to focus on is the situation where we have a ring that is commutative and has unity. We're going to explore some examples for now of rings that are not commutative because some people are interested in those. I've known people whose research was on non-commutative rings or things that were kind of close to being rings but weren't exactly rings. They were called near rings. We won't talk about near rings in this course, but you may wonder about what those are. So there are rings that are non-commutative. There are rings without unity, but most of the work that we do in ring theory uses both of these properties extensively. So a ring doesn't have to have these, but most of the rings that we will care about do have these.